Okay, so I'm typing, so it's going to sound a little bit stilted because I'm talking a little bit to the tape. But we are starting. This is just a review for the final exam, which is on Monday, December 12th, right at noon. Not at 11:30, but at noon to 2, and it is comprehensive. Um, So if you have to take the final exam, just keep in mind that it can cover material from the entire course, right? But so I have posted that final exam two on Blackboard, and also now posted the answers were posted this morning. So that's in the sample test folder on the Blackboard page for the class. And so that review really is a good summary, I think. The problems on that review is a really good summary of sorts of things that you expect to see on the final. So that's really good focus for um, reviewing for the final. But then don't forget, with that review in mind, you may also want to look back through your previous tests and your previous sample tests and so forth, notes to get ready for the final exam. And don't forget, you can bring your survival card with you and your calculator just like usual. So the final exam will be very similar to the previous test that you did a card. Okay. All right. So that's how things are going to work on um Monday. We have a couple of homeworks that are still due, so remember to finish these. There's the homework on polar coordinates and this homework on triple integration. So these are important now because these were not on the third test, but they can be on the final exam. So when you look at the final exam review, for instance, you're going to see problems like polar integration and setting up triple integrals to compute volumes of solids, like we use double integrals to compute volumes of solids. Um, and so there also is on the test 3 sample test, in addition to the final exam review, there's also on the test 3 sample test, there are some problems. I already started 15, so you missed all the important stuff. There are some problems on that test 3 sample test. There are some problems on polar coordinates and also on triple integrals. So you can look at those problems too for these topics in preparing for the final exam. But don't forget to finish these homeworks. I moved this polar coordinate homework back to due on the day of the final exam. That was due today, I think, originally, but I moved it back to Monday. There's no reason to rush to finish it since you won't be tested on this until Monday anyway. So this and triple integrals due on Monday at the time of the test. So because I want you to get finished with these as much as you can before you actually come to take the final exam, right? Because this stuff will be on the uh final exam. So I was just reminding Fatine to look at the final exam review, and the answers to the final exam review are now posted, and we will go over a few of those today. And then also we're going to go over test number 3 today, which I gave you back. Just some of the problems that were the most troublesome for students on the test number 3. All right. Um, so don't forget to use the final exam review to prepare for the final exam. The final exam review answers are posted. I hope the solutions are correct. I did them very quickly and didn't really double check them, um, but anyway, they are there. Um, okay. So do y'all have any questions uh, right now on how things are going to work? Um, don't forget also your calculus flux, right? So you can turn that in if you have flux dollars. Those are updated on the WebAssign. So you can turn that in at the time of the final exam too. If you have questions about that, then um, after the final exam, we can talk about how to fill that sheet out if you're confused about that, or before the final exam, if you get here early enough. Okay, so let's look first at the test number 3. So the test number 3 answers are posted. So that's what I'm looking at here are the answers to the test number 3 that are posted on the Blackboard page. And this problem number 2 is using the second partial derivative test to find, I think in this case, it's a local maximum on the graph of this two variable function. So most people did this. This was also what was in the first problem on the test. And most people were doing that well. Okay, so so that was good. The only problem, the only issue that came up in this problem is um, most people forgot, or a lot of people forgot to actually apply the second partial test to this problem. So what I mean is, so here's this function, which is the output here is the range of a missile when it's fired, and the x is the what? What does x represent in this problem? What does it say? It's the temperature, and the y is the humidity. So apparently the temperature and the humidity affect how far that missile can fly, right? The range of the missile. And what we're trying to figure out is what are the optimal conditions? What's the optimal temperature and humidity for the missile to go the maximum distance? All right. Um, and so this is just finding a maximum, right, on this surface. So so you guys know how to do that, right? So you're going to take the first partial derivative with respect to x, right, and set that to 0. And then you're going to take the first partial derivative with respect to y, right? And everyone was pretty proficient at finding partial derivatives, so that's good. Set that also equal to 0, and then solve this solve the system of equations, right? And that gives you your critical point, and then you can check to see if that's a maximum. So in solving the system of equations, let's see, how do we do that here? I think I took that second equation. Yeah, I took the second equation and well, first I moved the constants in the equations to the right-hand side, okay? And then I reordered the terms on the left-hand side, and then I multiplied the second equation by -1 on both sides, right? So that gave me plus 6x plus 6y equal 300, and then added this equation and this equation together. That's called the elimination method, if you remember solving systems of equations. So I added these two equations to the first equation and the bottom equation here together. And the reason I did that is because, of course, the y's are going to drop out, right, when you do that. And then you just get minus 2x is equal to minus 380 plus 300, which is minus 80. And then just divide both sides by -2. So you get the x coordinate of your critical point is 40. And then I think I just took this x value and plugged it back into this first equation, solve for y, and we got y is equal to 10. So the y coordinate of your critical point is 10. All right. Most people stopped right there. Okay. But you really technically have to check to make sure that the critical point is a maximum, right? Okay. So you do need to apply the second partial derivative test, right? So you compute the second partial derivative with respect to x. That turns out to be just a constant -8, which is less than 0. That information is important to us, right? Here's the second partial derivative with respect to y. That turns out to be a constant -6. And then the mixed second partial derivative also turns out to be -6, right? So remember, you use those values in computing this number called d, right? Which is part of the second partial derivative test. So that is I'm sorry, f sub xx times f sub yy. So -8 here times -6, and then minus the mixed partial derivative squared, right? So you end up with -6 times -8 times -6, which is positive 48, and then minus the -6 squared, which is positive 36. So you get 48 minus 36, which is, oh, this got cut off the scan, but that's 12. All right, okay, and which is positive, right? Okay, so that tells us, what does that tell us there? That we have a maximum. Is that right? Or is that backwards there? Well, that's the part of the test, right, that you need to that's the part of the test, right, that you need to use. Okay. Oh yeah, I forgot. The D is positive, and the second partial derivative with respect to x is negative. That means that our critical point is a maximum, right? Okay. Um, so when this second partial derivative is with respect to x is negative, but this d value we compute is positive, that means we have a maximum. If this were positive, if a second partial with respect to x is positive and the d value is positive, then we would have a minimum. What happens if d is negative? Do y'all recall? What sort of point do you get in that case? That's a saddle point, right? Okay. So if the d turned out to be negative, we would have a saddle point. But it's not negative, it's positive. So we're either going to have a maximum or a minimum. If d comes out to be 0, remember, that means that the test failed. So you have to go, you have to resort to some other method to figure out if you have a maximum or a minimum, right? So this is what people left off sometimes and lost points on that. They forgot to actually go through the second partial derivative test to demonstrate that this is actually you have a maximum when x is 40 and y is 10. Okay. Now, most people did really good at just evaluating the double integral here. Okay. So that wasn't really setting up the double integral, right? That was just evaluating it. And the answer turns out to be 18 here. So most people did this fine. If you did not do that, I think you can read the solution. If you did not get that right, you can read the solution. It's pretty detailed here. So review that solution on the answer sheet. I'm not going to go through that one. But on the rest of the integrals, okay, this is where most of the points were lost. All right, so this is something that probably you'll need to review for the final exam. Okay, so you don't miss the double integration, but don't forget also on the final exam will be polar integration, right, and triple integration. Okay, so be sure to look at that. Right, if you were not doing well at that, go back and try to learn that better. This problem now, though, is really not any computational work to do. All we were asked to do is to sketch the region, right, that is represented by the limits of integration in this double integral. Okay, so you just want to look at the double integral and see if you can find the region of integration, right, that the limits of integration are referring to, correct? Actually, since the integrand is 1 here, right, that means that if you actually evaluated this double integral, which you didn't have to do, but if you actually evaluated this double integral, since we have an integrand of 1, that means that what you'll come up with is the area of this region, okay? Remember, that's how you find area of region is find the double integral where the limits of integration match the region, and then just use an integrand of 1. And if you evaluate that, you will come up with the area of the region. Similar things happens for triple integrals too. We'll mention that in just a second. Let me lower the screen here so I can write a little bit better. And let's talk about how I ended up drawing that region, right? Did y'all get that one right? Why did you get it right? Yeah. Did you get it right? 15? Okay. All right, 15. All right. So we're concentrating on you. Look, since our in our order of integration, we're starting with y first, right? Think of these limits of integration, right, as equaling to y, and think about plotting those two curves. Okay, those are just straightforward functions, right? Okay, in the xy plane. So those should be pretty easy to graph for you, right? Y equals -2 is going to be a constant, right? That's going to be a horizontal line at y equals -2. So that's why I drew this long horizontal line here across here at y equal -2. And then you have to graph y equal x squared, but y equal x squared, that's just a parabola. There, it's this curve, okay? Um, this curve is y equal x squared, right? You know, when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 4. So you can plot a few points there on the left and right side of the x-axis, right, to draw that parabola, okay? So y is going to start at -2 and go up to x squared. So you know you're going to get this area between these two curves, right? But that's an infinite region between these two curves. So you have to limit it somehow, right? That's where the second um, limits of integration come into play, right? So since in the second limits of integration, we're integrating with respect to x, right? Think of this limit, think of these two limits of integration as being set equal to x. You have x equal -2 and x equal 2, and plot those two curves, okay? Well, those are going to be x equal 2 and x equal -2. Those are going to be vertical lines, right? When you have x equal to a constant, you get a vertical line. So you're going to get a vertical line through x equal -2 and a vertical line through x equal +2, right? And you want from -2 to +2, so you want the region between those two vertical lines. Well, put all that together, right? So we had the area, the region between y equal -2 and y equal x squared. So that's this part, right? But then only from x equal -2 to x equal +2. So you just get this little piece here that I've got shaded, right? Does that make sense now? Okay. Well, so if taking limits of integration and converting them to a region, yeah, this is simple. This is as it turns out, it's vertically simple. It's not horizontally simple, but it is vertically simple. If that's difficult for you, then that's what you need to practice, because because in setting up double integrals, you have to do it backwards, right? You have to take the region and convert it to the limits of integration. Instead of here, we took the limits of integration and we drew the region. But when you're setting up a double integral, you're going to be doing this in reverse. You're going to be looking at the region of integration and trying to write down the limits of integration. And that's what's really crucial. Okay. Well, let's look at number 5 then. Similar to this, right? Here, here the region is described in words for us. Here the region is described in words for us. So let's draw a picture of that and then see if we can set up this double integral to match that region, okay? Because what we want to do is integrate this function, sine squared x plus y, over this region that's described to us. Well, let's see. So this is the region bounded by these 4 points. So all you really need to do is plot those 4 points, right, in the xy plane, and then that will just show you what the region is, right? 0, 2 is right here. 4, 4 is over here, so I plotted that point. 4, 2 is right there, correct? And 0, 4 is up here. So when you plot those 4 points, you can see, oh yeah, those are corner points of a rectangle, right? So just connect those 4 points with horizontal and vertical lines to get a rectangle. That's going to be your region of integration. Now, how do we convert that to a double integral? So how do we take that region and convert it to a double integral? Look, the part of this is easy though, Fatim. You're integrating this function, correct? Sine squared x plus y. So that's going to be the integrand. So you just copy that in there directly. All right. And now what about the order of integration? Well, you can do it dx dy, or you can do it dy dx. You can really do it either way, just whichever is most convenient. I don't think it really makes that much difference for this region of integration, because this is a very simple region of integration. So I just chose dy dx, right? Okay. So if you choose dy, right, that means you're going to let y vary first. How does y vary, right? In how does y vary in this region? Where does y start and where does it finish? Bettine. What's the smallest in this region? What's the smallest value for y? 2. What's the largest value for y? 4. Right. So your limits of integration, if you start with dy, will be 2 to 4, right? Because this region is going 2 to 4 on the y-axis. What about now? Since we started with dy, then this has to be dx. What are the limits on x? So how does x vary in this region? From what to what? It starts, where does x start at here? No, x. Look on the x-axis. Where does this region start at on the x-axis? 0. And how far does it go on the x-axis? 4, right. So that's why we have 0 to 4 here. See that? If you put dx dy, then you would just reverse these, these limits of integration. So a rectangular region is really the easiest region to integrate over. Okay, all right, because for a rectangular region, it will be easy to set up the limits of. It'll be easy to set up the limits of integration. Well, that's exactly now what we faced here in problem number 6 and in problem number 7. So this is where we lost a lot of points, okay? So we have to set up a double integral to represent the volume shown here, the volume of the solid shown here, right? So you can see what we're talking about is this is going to be kind of a pyramid-shaped object, right? Or a prism-shaped object, right? We want underneath this plane, this is a plane, right? Down to the XY plane, right? So here, Bettine, is your region of integration. I can outline it here, but you can see it. Your region of integration is bounded by the x-axis and the y-axis and this line right there. See that little triangular piece in the xy plane? That is your region of integration. If you want to, you can go separately and draw the xy plane as you're normally drawing it, right? And redraw the region of integration. So what does that look like? We take this and draw it the usual way. What does that region of integration look like? Let's see. What points are we connecting here with this straight line? What is that on the x-axis? That's what? No, can you see? You can't see that? 4, yeah. So we're going up to 4 on the x-axis, and what about on the y-axis? 2. So put those together, connect these points with a straight line. See, that's going to be your region of integration, okay? The XY plane, that's this little region in the XY plane down here, okay? Now, however, we need to figure out what is this line, okay? So what's the formula for this line, all right? Of course, we could just figure it out from just using algebra, right? Because we know the x-intercept is 4 and the y-intercept is 2, but you don't need to do that, okay? Because you can get the equation for this line. That is going to be the trace of this plane in the xy plane. That's where this plane, right, intersects the xy plane, okay? And you find that by setting z to 0, right? In the xy plane, z is equal to 0, correct? So just take your formula for the plane just take the formula for the plane, which you're given there, fortunately, z equal 4 minus x minus 2y, and set that to 0. That's what I did there, Fatine. Just set that to 0. And I just happened to solve this for x because it was easy to solve this equation for x. So we get x equal 4 minus 2y. Okay, so that's the that's the equation for this line, x equal 4 minus 2y. But if you want to, you can also solve it for y, which is normally the way you would write it. I just solved it for x because I didn't want to have any fractions. But if you solve it for y, let's see, you would get what, isn't that, if we just rearrange things, I think we have y equals 4 minus x over 2. That's the solve for y. All right, so there's our region of integration, right? There's formula for this line. We can write it in a couple of ways, right? There's the equation for this line. We can write it in a couple of ways. And so that's really enough now for us to set up the double integral, okay? This is enough to, this right here is enough for us to set up the double integral. So what will the double integral look like? Well, you know, you've got your double integral, right? Okay. And then the integrand is going to be just the formula for the plane, which is 4 minus x minus 2y. You don't have to write z equals. It's just 4 minus x minus 2y. Okay. So solve for z, but don't write z equals, just write the expression with 4 minus x minus 2y. But make sure you have the formula for the surface solved for z. Make sure it's solved for z, right? Which this one already is, so easy. Now, the only other thing you have to choose is what's the order of integration you want to use. Do you want to use dy dx or you want to use dx dy? I just went with dx dy. Okay, so when you when you go with dx dy, right, that means you're gonna fix a value for y, right? So choose a specific a constant for y, and then you have to think about how x is going to change, right? So I picked a value for y, and over this region of integration, how does x change if you fix that value for y? Well, where does x start at? On the left-hand side, where does the x start at? No, 0, x, x, x. Where does x start at? On the x-axis, you're starting at 0. And where does it go up to? It goes up to right here, right? It stops right there. But what is that? Oh, I know. That's 4 minus 2y, correct? Right? Okay. Because the formula for that line is x equal 4 minus 2y. So your limits of integration for x here are going to be 0 to 4 minus 2y. Okay. Now, where does how does y vary? Well, you can see it here, correct? Right? Okay. Where does y start at? 0, right? And goes up to 2. Yeah. Okay. So that's why we have 0 to 2 here. Now you could have done it the other way with the limits of integration, right? You could have done dy dx. How would that have changed your double integral? Well, the integrand stays the same. It's still the formula for z, so keep that the same. But since if you choose dy as the inner order of integration, these limits of integration have to represent y values, correct? So in that case, you think of, okay, first I'm gonna, let me do it here. First, I'm gonna choose a constant value for x. And when I choose a constant value for x, how will y change? Right? So where does y start at, Fatine? Y along this line. No, where does it start at? On bottom. See, if you're moving along this vertical line, the y values start. Okay. You're moving along this vertical line, so you fix x as a constant, right? Where does the y start at? Points on this vertical line. Y start at. It's the smallest y value. 0, right? And goes up to where? This line, correct? But what's the form of that line? Be sure you have it expressed in terms of y. It's going to be minus x2. If you choose this, choose a constant value for x, the highest y pool is for I p minus x2. So in this case, you start with dy, you're going to go from 0 to minus x over 2. Now, how does x vary? It's pretty easy. X starts at what? Goes to that. Are you able to do on a test? Let's try again. On what looks to be a harder problem, but it's really not. Okay, really not hard. It's because there are some curves in there. Don't let that be confusing to you. Okay, so the formula for that surface now is 2x squared plus y plus z squared equals 2. So we have that written in a general form, but want that the formula for that surface, remember, want it solved for z. So I'm going to have to rewrite the equation. So take that equation and solve it for z, right? So you see what I did? I subtracted 2x squared and the y from the right-hand side, right? So I got z squared equal 2 minus 2x squared minus y. But that's z squared, so I want z. So I have to take square root of both sides. Now, normally when you take square root, of course, you would get plus or minus here, correct? But look at your surface. We're only on the positive part of the z-axis, right? We're above the xy plane here, right? We don't have any of this surface below the xy plane. So you can drop the minus. It's not necessary. So we just get z is equal to square root of 2 minus 2x squared minus y. That then is going to be, see, that's so easy. You can fill that in immediately, right? That's going to be the integrand, right, for your double integral. So put that right in there. And now you just have to figure out the region of integration. Okay. You can see it here. You can see it here in the xy plane, right? It's the region bounded by, this little piece of the x-axis, right? And then this curve. So there is your region of integration. You want to draw a picture of that? Let's draw a picture of that in a more standard way here. So let's draw the xy plane like we're used to seeing it normally, right? So that region of integration, you can see it here. What are its limits on the x-axis? -1 to 1? To +1, right? And then on the y-axis goes up to that's 2. And of course, you're going to connect these points with a parabola, I think, like this, right? That's what the looks like. What is now, however, we need to know what is the formula for this parabola, right? What is the formula for that parabola? We're going to have that. So how do you find that, of course? That's just the trace of this surface in the xy plane. So what do you do to find that? Set z equal to 0, right? Now, look, Mariah, I don't set z equal to 0 here. It's easier if you go back to the original equation. These two equations are the same. So just go back to the original equation and set z equal to 0. And notice what you'll get is, I didn't show it here, but you'll get what? 2x squared plus y plus 0, right, is equal to 2. Or in other words, just 2x squared plus y is equal to 2. And then if you solve that for, it's so easy to solve this for y. So I solve this for y, I get y equal 2 minus x squared. So there is that, there's the formula for that curve, y equal 2 minus 2 x squared. Oh, so let's use that in setting up the limits of integration, because that's so easy. Y equals 2 minus 2x squared, right? Okay, so if you use this equation, Fatine, that we have solved for y, that means you're going to start with dy as your inner limit of integration. And how, so that means we're going to think of fixing an x value and letting y vary with that fixed x value. So where would y start? On this vertical line, fix an x value. There's y starting. It's the lowest y value on this vertical. 0. Lowest y value, that's the highest. So it's up here, this point, right? What is that point? What's y at this point? Y is what? Minus 2x squared, right? This point on the curve. So your limits in 0 to 2. How that's easy, that's x. How does x change in this picture? X starts at those two. You're out of the is. So not evaluating that, fortunately. That might be challenging to evaluate, right? But we're not evaluating that. Just setting it up. Now, we could also set it up with dx dy. That's going to look really messy, though, right? Because I'm going to have to take this equation, Fatine, and do what? Solve it for first what? Not solve it for y. If I want to switch this to dx dy, I would have this, take this equation and do what? Solve it for what? X, right? And since the x is squared, that's going to give me a messy, that's going to give me a messy expression. So I didn't write that down, but we could. It's just going to be ugly, all right? If we do that. Okay. All right. So, well, I hope that helps you a little bit. So look for some more problems where you're asked to set up double integrals. You may look on the test number 3 sample, for instance, the test number 3 sample, and also on the final exam review, there are questions of setting up double integrals like this one. So look at those. And you can also go back to the homework on double integrals as well. All right, one more. So most people did good on this one, except they just forgot the last step. So here we're finding average height of this plane. This is a plane, 20 minus 2x minus 2y. So when you graph that surface, you get a plane. And so we want to know what's the average height of that plane above the xy plane, above the xy plane. What's its average height above the xy plane? Over this region, the xy plane. Notice that's a rectangular region, but so nice. Okay, so rectangular region, so you just want x with 0, y with 5. So in a rectangular region of integration, it's very easy to set up the, you don't have to go through all of this confusing examination of curves, right? To set up the integral. So this rectangular region, x is going to 1, right? And y is going to 5. So you get this little thin strip like this as your, you get this little thin strip like this, right? As your region of integration. So to find the average height of the plane, that means you integrate this, you find the volume of this object over this region, or the volume beneath this surface over this region, and then you just divide by the area of this region. So to find average height, find the double integral, and then divide by the area of your region of integration. But what's the area of that region? Of course, Patine, it's a rectangle. So what's its area? It's the area of that rectangle. What? 1 times 5, right? Which is 5. Yeah. Okay. Right. So when we compute the double integral at the end, we have to remember to divide by 5. That's what most people forgot to do. So they calculated the double integral correct, which is good, got 70, but then they forgot to divide by 5. So there is the double integral. I went with, in this order, dy dx. There's the formula for my surface, right? Because we have z equals. So I don't have to solve for z. Z equals 20 minus 2x minus 2y. Since I'm going with dy first, my limits on y are 0 to 5, right, in this region. And then for x, my limits on x are 0 to 1 in this region. And then we just evaluate that double integral. And you can follow those steps pretty easily on the answer key. You'll see eventually it arrives at 70. But then we have to divide the 70 by the area of the region to get 14. So the average height of this plane above the xy plane over this region turns out to be 14. Sometimes it's higher than 14, sometimes it's lower than 14. On average, though, its height above that region is 14. Okay. So those are the ones I think were the most, those are the ones I think on the test number 3 were the most troublesome. You'll have questions, more questions on test number 3? Okay. Let me stop here for just a second. And so I'm going to pause the recording here for a minute, and then we're going to come back and look at the final exam review. So I want to go over a few things on the final exam review just to highlight some key things there to prepare for on the final exam, especially polar coordinates and triple integrals. Okay. All right. So let me pause here for a second, and then we'll start up again in 2 or 3 minutes here. Just going to go get a drink of water. So I'll be back. All right. Let's resume recording here. Let's switch over to the, let me see if I can find it. Switch over to the final exam review. Oh, there it is. Okay. So let's look at some problems on the final exam review. I'm not going to go back through any of the kind of vector problems, but but you can look at the final exam review, and it gives you a good guide as to the type of vector problems you might expect. So be sure to review these types of problems. So in the very first problem, right, when you have forces, independent forces acting on an object and trying to find the total force acting on the object, right? Okay. So remember those problems, and then plotting vectors and doing operations with vectors, right? Remember all these sorts of things you can do with vectors: adding, finding the magnitude, dot product, cross product, right? Okay, all of those vector operations. So so be careful about those. Finding the angle between two vectors, that's useful. So you may want to look at that. Remember how to project one vector onto another vector. So projection, these are things you might want to put on your survival card. Formulas you might want to put on your survival card. Remember how to find a vector that's orthogonal to two given vectors. That's easy. That's just the cross product. Remember, is the cross product of two vectors is perpendicular to the two vectors, both of the two vectors, right? And then, using vectors to write down formulas for planes and write down formulas for lines. So be sure you have those types of problems. And then finding slopes, right, of surfaces in particular directions. So like problem number 8, and then don't forget about the gradient vector, right? The gradient vector, that's the vector that gives you the direction of maximum slope, right? So So remember gradient vectors. Um, and remember the slope, I'm sorry, the magnitude of the gradient vector is uh, that's always going to be the maximum directional derivative, right? What now? 25%, yeah. Yeah, 25%, yeah. Okay. So this is good stuff to remind yourself of and to write down on your survival card, right? Okay. Um, this is stuff you might have forgotten. So be sure you review these important types of problems. But the final exam review gives you a good summary of, I think, everything, but in particular, right, vector type problems and how, and then how we use vectors to write down formulas for lines and planes, and then how we use vectors to find directional derivatives, right? The derivative in a particular direction on a surface. Okay. Now, a lot of the final exam review is stuff that we just talked about on the test number 3 review, so I don't need to go back through that. But there are problems on here, right, on double integrals. So this would give you some more good practice on double integrals. But let's skip down now to what would be new on the final exam, and that is converting to polar coordinates. Okay. All right. So that's like problem number 15, and I think also problem number 16 on the final exam review. So definitely want to make sure, right, that you've reviewed these things and finished your polar coordinate homework, right, and your triple integral homework. All right, so this is a basic kind of problem. So in polar integration, so let's see if we can get through this one. So here's a double integral that we want to evaluate, but it's given to us in just rectangular coordinates, x and y coordinates, right? So we're just trying to find the volume beneath this surface. That's a plane. A volume beneath this surface above this region in the xy plane. That's the physical interpretation of that double integral. Let's see what that region of integration looks like. Okay, so let's try drawing a picture of that region of integration. So since our order of integration is dy dx, right? Let's think of plotting y equals 0 and y equal the square root of 1 minus x squared. And then, of course, we will limit that region of integration to only 0 to 1 on the x-axis, right? Because those are our outer limits of integration. All right, but first let's look at these two curves. Well, of course, y equals 0 is just the x-axis, right? So your region of integration is going to be bounded below by the x-axis. That's y equals 0. And then above, it's going to be bounded by this curve, y equal the square root of 1 minus x squared. So what does y equal the square root of 1 minus x squared look like? Well, if you square both sides, you get y squared equal 1 minus x squared. And then if you bring the minus x squared, I left it off here, but if you bring the minus x squared to the left-hand side, get x squared plus y squared equal 1. That is a circle. That's a circle. And that's a circle with radius 1, because 1 is 1 squared. So that's a circle with radius 1 and centered at the origin. So you get this circle, but remember, we had y was positive square root of 1 minus x squared. So that means we only get the top half of only going to get the top half of the circle here, right? Okay. So your region, so just looking at these limits of integration, you can see your region of integration is just this semicircle, right? The top half of the circle, but we only want x to go from 0 to 1. So we actually only get the right half of this semicircle, just this quarter here, right? From x equals 0 to x equals 1. So not the whole top of the circle, but just the portion that's in the first quadrant. So there's our region of integration. That's what it looks like. Now, the reason you want to draw that picture is because we want to convert this to polar coordinates. So we want to think of what does this region look like in polar coordinates. Remember, in polar coordinates, you have a point, right? And remember, the coordinates of your point are, in polar coordinates, are r, which is the radius away from the origin, right? The distance away from the origin. And then theta, which is that angle that point forms with the x-axis. So in this region, how can we describe points in this region? Well, notice, right, a 15, what's the maximum distance any of these points is away from the origin? What's the maximum r value here? What's the smallest r value? So what did I do? What's the smallest r value? Am I in the right section? There's sample test number. Where did I? There's test number 3. Oh, shoot. Oh, did I lose my? I don't know what I did here. I lost my up there. Oh, phooey. Wait a minute. Let me try fixing this. Okay, I think I recovered it. What we were writing a moment ago, whatever that was, I lost, but that's okay. That was very little. Right here, right? Yeah, I remember this was supposed to be x squared, correct? So in this region in polar coordinates, right? The 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 restrictions on the distance away from the origin, well, the smallest distance would be 0, right? And because you can be at the origin, but what's the maximum distance these points are away from the origin? Well, you have 1, right? Okay, because you're just going out to this circle, which has radius 1, right? So the limits of integration on R would be, or the limits of integration on R for this region are 0 to are just 0 to 1, right? What about for theta, which is the angle formed by the point and the x-axis? Well, since you're in the first quadrant, all your points are in the first quadrant, right? What are the limits of angles in the first quadrant? What's the smallest angle that's in the first quadrant? That would be an angle that just lies along the x-axis. So what's that angle? 0 up to pi over 2, right? So the limits on theta are from 0 to pi over 2. So you see, it's very easy to look. Here's the advantage of polar coordinates. It's very easy to describe that region in polar coordinates. See, in rectangular coordinates, the limits of integration look kind of messy here, right? Because they involve this square root. But in polar coordinates, the limits of integration are very simple, just this. Okay, they're constants. So what does our double integral look like in polar coordinates? Well, here are your limits of integration. R goes from 0 to 1, and theta goes from 0 to power 2. In polar coordinates, you usually almost always have dr d theta, that order. Okay, r comes first, theta comes second. So theta, r only goes from 0 to 1, theta only goes from 0 to power 2. Now, what does the integrand look like? Well, remember, the original integrand, right, was 3y, correct? But what does y look like in polar coordinates? Remember, that is r times sine of theta. Convert y to polar coordinates, it's r sine theta. Y is r sine theta, and x is r cosine theta. So we just have to take that y and write it as r sine theta. But the other trick in polar coordinates, when you set up the integrand, you have to put an extra factor of r. So that's always required. So that's why I multiplied in extra r. So there is our double integral that is the same as in polar coordinates. That's the same as the double integral in um, rectangular coordinates. And now we just have to evaluate that. So I'm not going to go through the steps of the evaluation. It's like I messed them up to start with there. Okay, so just go through the steps of the evaluation. You can follow that. That's just calculus. Okay, and it works out very nicely if I did this correctly. Just eventually a 1. Okay, so you have it here. Sure. Make sure you know how to find the antiderivative sign. The antiderivative sign, though, I think it's minus cosine. So antiderivative of sign minus. So, anyway, 0. Oh, thank you. I wrote this down. I wrote this down. That's a 1. Otherwise, it's not 0. So, okay. My mistake. Okay, so I think it's 1. Maybe I still have a mistake. If you find that mistake, that would be good. So kind of get the idea there. Let's try it again. Same type of problem. I just have a different region of integration. So this region of integration is very hard to write down in rectangular coordinates. So we're just going to write it in polar coordinates to start with, but it's very easy to write in polar coordinates because you have this is called an annulus. It's a region between two circles, right? Shaded area between these two circles. So that's very easy to write in polar coordinates. Because remember, looking for what are the limits on radius. So for in this, it's called an annulus. For points in this annulus, what is the it's on the radius? How close are those points to the origin? It's the smallest. That would be along the circle. What are these points are what distance? See if they're 2. Yeah. These points are 2, and these points are what? So you're looking at points or between 2 distance away. So their radius would be 2. Now what about for theta? So look at these points. There are points in the first and second quadrant. Second quadrant. It's the smallest thing. 0, right? That's the x-axis. Up to, that's the biggest thing that you could have. That's the left side of the x-axis. Right? So, so your angles are varying there between 0 and angles are varying between 0 and pi. So easy now to set up your polar integral because there are your limits of integration. The only thing you have to figure out is, how do I take the x squared and plus the y squared? That was the formula for the function, right? How do I convert that to polar coordinates? Because I can't have it x, y, so I gotta have it in theta. But again, there's a conversion formula. You have to remember this famous formula. R squared in polar coordinates is x squared plus y squared. Usually that's written a little bit differently. Usually you see that written as r is equal to the square root of x squared plus y squared. But of course, if you square both sides, you just get r squared is x squared plus y squared. Oh, so where I had x squared plus y squared, I just put in r squared. But now, don't forget, always in polar coordinates, you need an extra factor of r. So be sure to put that in your integrand in polar coordinates. You need an extra factor. So you end up with r cubed here that you're integrating. Oh, that's so easy to integrate now, right? So there are the steps for evaluating the integral. So I don't need to go through those arithmetic steps. I think that okay. In the copy one, I came up with 65. Sure. Check. Now, another thing you can do with polar coordinates. So remember, there are other problems like this on the test number 3 sample. Test number 3 sample, the last few problems, I think it was 11 through 14, on test number 3 sample, those are also about polar coordinates and triple integrals. So you can go back and look at those problems on the test number sample, still posted right on, and get some more examples. But you're also doing that polar integral homework, which is due on Monday also. So that also will have sample problems. All right, now let me show you another type of problem that seems like it's a little bit more difficult, but it's really one thing polar integrals is really useful for is finding areas of regions in the plane. Remember, we can use double integrals to find areas of regions in the plane. What integrand do we use in that case? If you're using a double just to find an area, not a volume, area, the plane, what integrand? That's right. Set up your limits of integration on your double to match your region in the plane, but you just use an integral. That's the same thing you do. That's the same thing you do polar find area. Okay, so we're going to set up double integration to match that region. Okay, that very strange region. Okay, that's one technique. And we use an integrand of point. But why is the R code? Because it's polar, right? So you do have an integrand of 1 there, but you always have to put in the times R. Okay, right? So really get an R. So we're not asked to evaluate this. So we really don't have any work. We could evaluate this. I don't think. No, maybe it's not so easy. But anyway, we're not asked to evaluate it. We're just asked to set it up. So the only real problem here is finding the limits of integration to match this region. Fortunately, we know what the formula for this curve is. Okay, if we didn't know the formula for that curve, we'd obviously be in trouble. But the formula for that curve is r equals sine 2 theta. So that helps us a lot. So if you have points exactly on this curve, so points that lie exactly on this curve, those are points that match this equation. So that means their R value is going to be exactly 4 times sine of 2 theta. Points on this curve, their radius will be exactly 4 times the sine of 2 theta. But we also want points inside of the leaf, right? Inside of the 4-leaf clover. So so that means their R value can be less than 4 times sine 2 theta. Okay. See, points on their radius is exactly 4 sine 2. inside of the light, and its radius would be less than sine. It's just less than. So in setting up the equation r going from 0, as that would up to is see, you can have points with radius 0 up to this radius, which is 4 sine 2 theta, but you can have any radius in between. So your r ranges from 0 to 4 sine 2 theta. Now, what about the angle? Well, here you get a break. All of these points are in what quadrant? Well, in first quadrant. So we got the point all right, and so that means our angle. That double input fitted the area of that on this curve. If you let your angle go from 0 to 2 pi, you'll actually get all 4 quadrants, of course, and so you would get a 4 length. Or think about that. You don't even have to pi. I'm sure if 0 to pi. Okay, so remember, you can compute areas of regions with polar coordinates, just like you can compute areas of regions with rectangular coordinates. You just use an integrand of 1, but don't forget you have to multiply it by r. Okay, guys, last problem. Ooh. Triple integral. Yuck. All right. So we're trying to find the volume of this thing. Okay. I don't know. In other words, volume of this surface down to the xy plane. So we know how to do that with double integrals. Let's have an example similar to double. Now we'll use a triple to find this same volume. I'm not actually going to compute the triple integral, but we just want to set up the triple integral. Yeah, that's right. So you're going to have a dx, a dy, and a dz. But look, let me give you a shortcut here for setting up triple integrals. So this is explained. You look at the test number 3 sample. Oh, I think that's, let's see if I can get to that. Test number 3. Oh, there it is. Well, I hope I can get back where I was now. All right, there's the test number 3 sample. If you go to the end of the test number 3 sample, see there's lots of problems on polar, so you can look at those. There's a really hard problem finding area with polar. There's one like that in your homework. But anyway, at the end of that sample test number 3, there are 2 problems on setting up triple integrals. And it gives you a little bit of a hint there on how to set up triple integrals. Or at least what's required to set up triple integrals easily. See what that hint is? It says we're looking for the volume of a solid that's beneath the surface of the xy. Okay, so if this is the simplest type of volume, you want the volume of a solid that's beneath the surface down to the xy plane, and it's easy to create a triple. Okay, it says this integration is going to be easy first, then dx dy or dy dx. the order of the y and the x is less important, but start with z first, okay? And then here's what you're going to do. So let's go back to, is that the right? Yeah. Let's go back here to this problem. So to set up the triple integral, what it says is start with z, okay? And then, so that means that use an integrander of one, just use an integrander of one, so you don't have a fancy integrator. Just use it like it's like an area. Now, for your z limits of integration, we'll start with 0 because we're looking uh, for a volume beneath the surface down to the xy plane, right? So at the xy plane, z is 0. And for the upper limits of integration, just use the formula for the surface. So the formula for the surface. Is it there? What was the formula for this surface? Was it z equals something? Ah, there it was. Z equal 4 minus x squared minus y squared, right? So we're just going, is that y squared? Did I leave off a square again? Oh no, just y, right? So so there's our limits of integration. Z just 0 to surface. 4 minus x squared. Now, what about for your x and y limits of integration? Just look at your region of integration in the xy plane, and then set up your limits of integration that match that or the double integral, right? Okay. So let's see. What is our region of integration here? Well, it's going to be what? This. It's going to be this little piece in the xy plane, correct? Between what? The x-axis and this curve. Between the x-axis and this curve. How do you find that curve? How do you find that curve in the xy plane? What do you do? Yeah, in your original formula, set z to 0. So there I have it, 0 equal 4 minus x squared minus y. And that's very easy to solve for y. So I solve this for y. So I get y equal 4 minus x squared. And that's why I wrote my second variable of integration as y, right? Okay, so I did dz first, always first for the triple integral. Then I did dy because my limits for y are going to be what? From 0 up to this curve, but this curve is 4 minus x squared, right? See, if you draw this picture of that region of integration in the xy plane, see, that curve looks like this. No, that's a really bad picture of it, but this curve in the xy plane, right, looks like this. There's our region of integration. And where does y, if we fix x, right? If we fix x, how is y varying? It's starting at 0 and going up to this curve, but this curve is 4 minus x squared. And then what about x? That's easy. X is going from what? -2 to 2, right? Okay. Z always, yeah, when you say all the way to the right. In this order, dz first, yes, in triple integrals. What now? Here, no, you can do dx or dy. You can do dy dx or dx dy. It's just whatever is easiest. But start with dz. Okay. Yeah. These, remember, the limits for x and y are just going to match your region in the xy plane, right? And then the limits for z will just be 0 up to whatever the formula for your surface is, right? Remember, you're going to set it up like this. Only if your volume is the volume beneath a surface down to the xy plane, right? Okay, but that's exactly what this picture is. And if you look back at that, is this sample test number 3? If you look back at this, no, this is test number 3. Where is this? Yeah. So if you look at these problems from sample test number 3, these are the same situation. Volume beneath the surface down to the xy. So problem C. And the dx dy just how you want to find it. So the region, so here the region that's our point is fine. Okay. So you look at the solutions there and see how I set that up. Yeah, I drew a picture of it. Well, you've also got a triple integral homework too. It's not very long. It's only got 4 problems on it, but you've got also some problems on your um on these two sample tests that you practice too. Okay, guys. I need to stop there. So give me time to process this video. I have to be somewhere at noon. So y'all have your index cards already for the final? Okay. Got 150? All right. So well, I'll see you on I'm gonna post this video so on the Blackboard page so you can look at it again if you need to. It will be right there with these final exam review solutions, which again I mentioned uh, are already posted on the Blackboard page. All right, let me see if I can stop this.